What's up, YouTubers? Jose Quiñones de Ciencia here. As you can see, I am in a little corner in my workshop where I've been building these walls, as you can see. So of course, I've been cutting a lot of wood with my miter saw, and as Murphy's Law would have it, the little rascal stopped working. Let me show you. I mean, it still cuts wood, but for whatever reason, it does this. For whatever reason, it does this. Okay, for whatever reason, it was doing the following. Literally, not even a week ago, I was cutting wood and the blade would not stop. It would just continue coasting, which is a known issue that happens with some of these pieces of equipment when the braking mechanism breaks. When the braking mechanism breaks. So the braking mechanism doesn't break, which means it's broken. You gotta love English. Anyway, I bought the switch because I know for a fact that the way that these power tools work is that there is an element inside of the switch to apply a short to the motor so that it stops quicker. And for whatever reason now the little bastard is working. So I don't know if it is the cold, but I gotta say I'm kind of pissed because I spent all day long recording the second part of this video. The first part was gonna be let's replace the switch, and it was gonna be a tutorial on how to fix your miter saw when it stops breaking. Look at that, I bought the freaking switch because this thing wasn't breaking. The second part of the video was gonna be about basically a little demonstration where I geek out and talk about how motors break and the science behind shorting the back EMF and that kind of deal. But you know, I guess we're just gonna have to go into the geeking out because I already recorded the video, so we might as well put it out there. And if you guys want to see a cool demonstration on the effects of shorting the electric circuit of a motor, basically shorting the back EMF so you can break your motor, let's go to the next part of the video. All right, so I have a setup here. Let me show you real quick what this is all about. I have a brushed DC motor with a gigantor wheel that I made on the lathe. It's basically a large mass so that the motor can stay rotating for longer. I have a voltmeter, and then we have a little lamp. And what I want to illustrate is what happens when the motor becomes a generator. So as you know, when you unplug the motor from the power supply, it switches from being a motor, and now it becomes a generator. So all of the energy, mechanical energy that is basically inside of it will now become electrical energy in one way or another. So I want to illustrate what happens when you take that electrical energy and you dump it into something. So let me show you real quick. If I plug the motor to 24 volts, you will see that the voltmeter is telling us what is the voltage. Now, as I unplug it, the motor is going to continue generating that voltage. So now that's not the voltage on the power supply because obviously the power supply has been removed from the equation. The voltage that you saw on the meter is the voltage that was being generated by all of that mechanical energy being transformed into electrical energy. Now, because the power supply had been removed from the equation and I didn't connect the motor lead to anything, the motor was basically just what is called coasting down. So all of that mechanical energy was being dissipated into heat through basically friction. And there might have been some electrical currents inside of the motors, like eddy currents and stuff like that. Those are very hard to measure because, of course, those happen inside of the motor, if anything. Mostly, however, it would have been friction and of course, you know, air resistance, but that would be so insignificant. So mostly friction. That's what eventually caused the motor to stop. Now, what you saw on the meter was the voltage of the motor, which is basically directly proportional to the motor speed. So when the motor was going at its maximum speed, the voltage was 24, but eventually it started going down until it reached 0 because the speed was 0. So what you saw on the voltmeter was basically the motor constant, the voltage to speed constant, so how many volts did you get per speed on the shaft, multiplied by the speed, and that gives you volts. Of course, as the friction made the motor stop, the motor came to stop and the voltage was 0. So now let's try something different. Now I'm going to spin the motor again. So we have the motor energized at maximum speed, and what I'm going to do, I have a lead here. This is very crude, so I apologize, I don't have anything ultra fancy, but the results are the same. I'm going to unplug the power supply and immediately connect the other side of that bulb. As you can see, we have light, and the motor is now powering that bulb, that light bulb. So I can assure you the motor stopped quicker than before, because now the motor was generating power. It was basically transforming its mechanical energy into electrical energy. It wasn't just the friction of the motor. You know, when I said friction earlier, I forgot to mention this is a brush DC motor, so there's going to be a lot of friction on the brushes. There is also going to be a lot of friction on the bushings, because this is not a motor with ball bearings, but if it had been ball bearings, there would have been some friction there as well. So the friction is on the brushes and on the bushings, but now we actually closed the circuit. We added a bulb, so that bulb became an electrical load. So now there was a current flowing to power the light bulb. So now the mechanical energy was able to become electrical energy to power the bulb. There was still friction, because that doesn't go away. There were still losses in the forms of heat. That also doesn't go away, but now we added more heat because there was current flowing through the wire. So all of those losses that are electrical losses now came into play. That made the motor stop quicker. All right. Now this lamp is not that big of a load. So that's why if I compare how long it takes the motor to stop without load or with load, it's not that much of a difference. And I'm going to show you the difference in a little bit. But let's do one last experiment. And this time I am going to spin the motor, and as soon as I unplug it, I am going to short its terminal against its other terminal. So in essence, I'm going to be shorting the motor. Let's take a look at what happens. Same speed as before, so it's maximum speed. This guy is moving on us. Now I'm going to short it. It stops immediately. So what happened there? In essence, I added the biggest possible load, which is, for all practical purposes, an infinite load. It's not an infinite load, but it's the closest thing to an infinite load. When I shorted the terminal, both terminals of the motor, call them the positive terminal and the negative terminal. When I shorted them together, what I did was that I applied a short to the motor winding. So now all of the mechanical energy that was inside of the motor generated the same voltage that we saw before, but the current was way larger. Why? Because the resistance was the smallest resistance possible, which is basically the resistance of the wires, the resistance of the windings, and anything else, you know, the brushes, the commutator, all of those resistances added together. That's the minimum resistance that we can put. You cannot put zero ohms. There is no way, because these are not superconductors. If I could put 0 ohms, this thing would, first of all, current would be infinity, which is of course impossible as well. But because there are resistances inside of the motor, the wire, the brushes, the commutator, and all of that stuff, that is the smallest resistance that we can put. So basically, let's say the resistance is 2 ohms, just to put a number. If the motor had 24 volts divided by 2, remember, current equals voltage divided by resistance, 24 volts divided by 2 ohms, that would have been 12 amps. So 12 amps were basically recirculated through the motor itself. And what those 12 amps do is that they generate a magnetic field that opposes, basically a revolving magnetic field that is opposing the one that it has to cause the motion. So those two magnetic fields fight each other off so fast because they're so big that the motor has to come to a stop. And that's how you break motors. You basically you create a short circuit in between the motor terminals. Now, that is the worst possible scenario, basically shorting the terminal, which is what the saw is doing anyway with that switch. I am not sure if there is a resistor in there, but if there is a resistor, that of course makes it a little bit better than just a short. Of course, the motor has a resistance, the wiring has a resistance, and all of that stuff. But if the switch has a resistance inside or not, I'm not so sure of that. But regardless, because you want the motor to stop so fast, the resistance would not be too big. If the resistance is super big, then it's going to take longer to stop, as you saw with the light bulb. The light bulb didn't make much of a difference because the resistance was fairly big. Basically, the current was not big enough to generate a revolving magnetic field that would stop the motor very fast. So when you put a load to stop the motor very fast, that load has to be fairly small. But as you can imagine, that means the current has to be huge. So that is why I call this the worst possible case scenario for the motor, because you are literally basically telling the motor to be subjected to the maximum possible current that it can be subjected to. Every time you break the motor and you shorten the terminals, you are taking all of that kinetic energy and in a single instant transforming it all into electrical energy, which is going to get basically transformed into an immediate form of power, which will stop the motor. But the amount of power is so large that the switch must be able to handle it. And even if you can do this a few hundred times, maybe a few thousand times, eventually the switch is going to get cooked. So braking is obviously something that we do with motors all the time, and you have to size your braking circuitry accordingly. But it is an incredibly strenuous situation for both the motor and the power stage. So it has to be done with incredible care. There is a good chance that you're going to cook something up, because the amount of energy that you are just basically dumping into the system is so ridiculous that if you don't size your power structures correctly, it's just going to fry. So before I go, let me show you real quick what it looks like, the three of them at the same time, so you can appreciate the difference in time. And of course, as you are able to see, the light bulb and the no load are not that different. It's just maybe fractions of a second difference. So the higher the load, the quicker it stops. But of course, the higher the loading scenario, the worse it is for the motor and the system. Now, of course, motors are pretty strong. Cables are usually pretty strong. So in this case, the limiting factor is the switch, which is why the switch died and it had to be replaced. So if you have any piece of equipment that comes with braking, that is basically put in place by using a switch to short circuit the motor once it's unpowered, be aware that the switch is probably going to die at some point in time, so you may want to have a replacement in hand, because power tools that have this kind of braking mechanism rely on that safety for you to be safe. So you would not want to use the tool without braking too much. You can still use it, and maybe you can use the same wood to apply some braking, but that's probably dangerous and not safe. So I would say change the switch as soon as you can, and basically put braking back into the business. So I hope this has been an enlightening, a quick little demonstration on how braking happens. And these tools, in a car, they don't do this because in a car you want ultimate safety, so that's why they use actual particle brakes. They may use a little bit of braking with electronics, but for the most part, you're going to have particle brakes. So in power tools, adding particle brakes is hard. That's why they use braking with electronics. So I hope this has been enlightening and you have enjoyed the demonstration. I want to thank you for tuning into my YouTube channel. I'm going to see you on the next one. Murphy, how on earth are you so good at always messing up my plans? This Murphy guy is quite tenacious.